that's basically what we're going to be doing today. A couple of things, guys. Let me move this one away right in here. Okay. So electrical symbols and outlets. You are all familiar with the outlets that we use in the industry. Anybody's familiar with this outlet? Used in Britain. So outlets are different. Obviously, we design systems in the US, but you might be able to work for an engineering firm that do design in other parts of the country. We're international now. So be aware that not all outlets are born alike. So we're all familiar with this type of outlet. This is equivalent to, this is 13 amps, equivalent to our 20 amps or 15 amps outlet. So I brought these ones, guys, for you to see. You're familiar with the switches that we have in the US. This is a switch that they use in England. That's equivalent to our 15 amp switch that we use, single pole switch. So these are all the outlets and the symbols that we're going to use. I like to bring them with me because it shows that when you work for an engineering firm, when you hear an outlet, if you're designing for a company anywhere in the US, you're good. But if you're designing overseas, pay attention to the type of the outlet that you're talking about. So that's a big deal. So what we're going to be doing, guys, is outlets and symbols for dwelling. We're not going to talk anything about non-dwelling, so don't mess with that one. It's coming. So everything that we're going to do is dwelling outlets. We're going to discuss the boxes that we use for dwelling, the switches, and the lumineers. So again, how do you put an electrical system for a house or an apartment building, right? You need a box. Inside the box, you're going to put devices. The devices looks like this as a receptacle, or it's going to look like these as switches, right? You're going to have switches inside it, and with these receptacle, you can utilize the power, as we all know, and with the switches, you can control the light. That's also utilizing the power. So that's kind of the big picture there. And in between, you're going to tie all these systems with a bunch of wires. That summarizes the whole power system in any building, residential or non-residential. So we'll talk about these one, guys. Different way of mounting things when it comes to electrical devices. Different methods of mounting that you can use. Dwelling, we're not going to talk too much about non-dwelling yet. Dwelling, most of it is non-metallic, right? Studs, wood studs, easy to use, non-metallic. I bet you 90% of what we do in dwelling is non-metallic. Boxes, and you nail them against the studs. So not a whole lot to it. A lot of you guys, you've done that with us, right? Most of you, if you haven't done, Aaron will take you to one of our labs and you nail a couple of boxes to the stud and you put a wire inside them and wire it. I like you guys to be able to wire at least one or two outlets. You're not going to be electricians or journeymen from this class, but you need to be able to wire. So mounting these devices, positioning the receptacle, you're going to decide the whole controversy with is the receptacle should be stand this way, that way, the other way. We'll talk about this controversial issues a little bit. Remodeling work, a little bit about remodeling work when it comes to residential. So these are the major things that we're going to talk about. Box fill. You guys have done box fill calculation. So what this book has, Jeff, I know you guys have done box fill calculation, but it has two tables that I thought it's better than anything that I ever seen in terms of summarizing the box fill calculation. I want to show you these two tables. If you want to know anything, just look at these two tables. It summarizes the whole box fill calculation to it. So it's really cool. Fire resistant walls. We'll talk. This is a big deal, guys. Ceiling walls. If you penetrate a fire resistant wall. Rule number one: fire resistant wall. You penetrate that one. You have to maintain the integrity of this wall. So if it's a 1 hour fire resistant wall, you're going to caulk it or put some type of insulation that maintains a 1 hour. That's typical for all the electrical stuff that we do. We're going to talk about this residential, but it applies also for any electrical systems that we do. We talked yesterday, guys, about electrical system. We're electrical designers, Aaron. You missed a little bit on, we loaded our symbols yesterday. Do you guys remember the symbol list that we loaded for you? So that's why. Why do we use symbols? Because we don't want to write encyclopedias. When we need a receptacle, we throw a receptacle. So we throw receptacles, we throw a couple of symbols on our plan, and these symbols will make what we call it our electrical power system, or our electrical lighting system, or our low voltage system, which is fire alarm, security, phone, and data. So we'll talk a lot about symbols and devices. I want you guys to pay attention to this boy here, outlet. An outlet defined by the code, this is big deal. Any place, an outlet, a location where you can utilize power, we can consume power. Right above your head is, these are called outlet, lighting outlets, because we're utilizing power as light. And all these receptacles that you guys are plugged in are outlets because we're utilizing power as, you're utilizing them through your computer, you're cooking your electronics. So there are two types of outlet, lighting outlet and power outlet. Everybody's is okay with that, that term outlet? Any place where you can we can hook into the system and utilize the power. What does utilize means? You're taking current and at a specified voltage. That's what utilize means. You're plugging things and you're running it through the electrical system. Any comments, guys? Any questions about the symbols and the term outlet that you're going to use? We're going to be using outlet a lot when we do estimation later on. So outlet, any place where you utilize power. Where with a utilizing device, with a device like a light, with an equipment like a light, or with laptops, you plug them in, so you're using electricity. That's your outlet. So an outlet could be feeding a receptacle, could be feeding air handling unit, could be feeding your light above your head, and so forth. Here's the symbols that we use, guys. You guys are going to be designing it, so it's a big deal. This is a symbol of a duplex receptacle, symbol of a light, three-way switches. So when you start designing with Chad, you're going to do the following, right? When we wire the system, let's just do it the way we design it first, and then the way actually we wire it. The way we design it, let's just assume, I want to assume just for simplicity that assume for simplicity, just for simplicity, that's my panel is located, this is my panel, located right here. And now let's do it as a designer. Everybody knows that this symbol of receptacle. If you don't know, we have a legend. You'll look at the legend. The legend's supposed to tell you what each symbol means. These are ANSI standards adopted by the engineers all the time. You're not supposed to memorize all these, but the more you use them, the more you get to know them. Okay, so when we design them, you guys put your receptacle. Suppose I want to put another receptacle here and another receptacle here, right? I designed the power outlet for this room, right? That's what you guys are going to do with me, except you're going to drop them in CAD. Step one, we do spaghetti we call it spaghetti in the residential. In the commercial industrial, we don't do that. But I want you to do spaghetti for one reason, because I want you to understand how the system is put together, electrically speaking, wiring speaking. So let's try it. So I decided I'm going to go, everybody's okay with that one. I'm going to decide also to put another can. Here's one can here, another can. And so I have 5 lights in this room. I overkill. Don't ask me how many. You need at least 1 light by code. I decided to put 5 cans in this room. Cool? Everybody's okay with that? 4 cans and a surface mounted light in the middle of it. Now I want to know, I designed it. You guys will drop them into your building. Now let's go wire them. Show them wiring wise. I decided, just for the simplicity now, to put 2 circuits. I want to put, let's just put 3 circuits here. I want to put all the receptacles in 2 circuits and all the lights in 1 circuit. That'll give me 3 circuits. We'll talk about circuiting in a second. This is just what you guys are going to be doing. So let's go do that. So I want to go to, let's start with the circuiting. Let's go, I decided to single-handedly to grab this receptacle and this receptacle and this receptacle and bring them into a home run. And this is circuit number 1 from P-1. So here's circuit number 1 from P-1. This is what they call a home run. You guys are familiar with a home run, right? You take a home run. What is a home run? A home run is a wire like looks exactly like this one. In this case, let's say this was a 15 amp circuit. That will be 14-2 conductors going all the way to from this receptacle to the panel. That's my home run. Then in between, with 14-2, I go to receptacle, this receptacle, and this receptacle. Why did I do it this way? I designed it this way. We'll talk about all the requirements for the code for residential as we move on. But this is just an example of doing that. Okay, so here's circuit 1. That's what you guys are going to be doing with me, except in CAD instead of drawing it. Let's do circuit 2. So I decided to do circuit 2. How many receptacles left? to spice it up, let's just put another receptacle right here. So look at that. I'm going to come right here, see with the red now to make it, and right here. And from here, I'm going to go with a circuit number. Okay, so now circuits are 1, 2, 3, 4, 5, 6, 7, 8 in dwelling, right? Always the odd numbers are on the left, the even numbers are on the right. Always. Okay? The odd numbers, every two adjacent ones will be coming from two different HOTs. We'll talk about this one. Let's just ignore all this one. I'm going to just call this is, I'm starting circuit 1. I'm going to make this a circuit 2 and panel dash 1. So this is circuit 2 going directly to panel 2. What does that mean? It's going to be landing on a circuit breaker like this. So I have two circuit breakers now feeding these two sets of receptacles. Any questions with that? You're familiar with that? Piece of cake, right? Let's do the third circuit. I'm going to use it with green just for the heck of it. So I'm going to go my third circuit. I'm going to go loop all my lights together. That's how you guys are going to be showing the design part of it. I'm going to loop all my lights and come over here. And from here, I'm going to come with my home run. Same thing, circuit number 3 from panel dash 1. So I have a home run coming to the light that feeds all these lights and, of course, the three-way switches. I have 3 circuits that feeds this area. Any questions, any comments? Everybody, that's what you guys are going to be starting tomorrow or Monday. That's what you're going to be doing in CAD. You're going to grab a wire and loop them together. This is the design part of it. Let's talk about the installation part. That's how you design it. Again, this is called spaghetti. We're going to do spaghetti for this project. We're not going to do spaghetti for next projects. We just specify the circuit right next to the receptacles. Any question, guys, about that? That's basically what the whole design is. Now let's go do actual wiring. Actual wiring. When you do actual wiring, you're going to move into the walls. I don't want to complicate the whole deal here, but let me just move with red here. The same red. You're going to come from here. So you're going to move into the wall. Look at that. I'm going right through the wall. That's where your actual wires are going to be going, right? All the way to here. Where else? No, I have. Now, when I reach here, I can't go because there's no continuous wall here, just based on what we have. What are you going to do then? You're going to go up, over. So remember, this circle means up, over. So I'm going to go over here, up and over, and continue into my panel and bring these 14.2 into my panel. That's how you physically, mechanically have to wire this baby. So you guys can imagine how the blue is going to be the same thing through the wall. You're going to move through the wall up to this point. I can't go through the wall because there's a door. What do? Go up, over, and you dump that circuit into the panel. We are moving with Romex. We're doing dwellings. We're roaming with Romex here. We'll talk about industrial wiring and commercial wiring in a few. Yes, sir, Darren?
I was just going to say, is the one that through each board all through the wall, and that's like 3 cables, you can fit through, when you're pulling your wire through the wall. Isn't it 3 cables that you can fit through?
One hole?
Yeah, before you have to drill another hole to run more cable around.
Because if you copy it, you derate. I'll get you in the derating. If you hold your horse on that derating, yes. And we will get into the derating, how many cables you can fit to derate. So that's it. That's basically what you guys are going to be doing with Chad. Any questions, any comments? Any questions, any comments? When we get into the derating, guys, we'll take this conductor that you're looking at, number 12, and we'll see when we do some derating, and you can see even if you derate at 50%, you're still pulling 15 amps out of that. So there's a good stuff coming. Okay, so that's basically what you're going to be doing for the symbols. Any comments, any questions? Aaron, doesn't make sense? Tying them together. So the dotted lines are actual physical mechanical wiring. The loops that I did, these are how you guys are going to show them to me. Spaghetti. We call them spaghetti. Now there are rules of how to wire how many receptacles. We're going to be going over them in a few. Okay, so that's basically, I thought just to throw this one. Okay, device and receptacle. Devices, this is by code called devices, guys. Devices, they control power, but they do not consume. Okay, these are called by code devices. What's the difference with device and outlet? A device does not consume power, but control power. Everybody knows that one? So that's your device business. Consume control power but does not consume it. Control power but does not consume it. Receptacle outlets is an outlet right in the front of you. At the end of that outlet there is a receptacle. You guys are all familiar with the receptacle 120. The receptacles can be 120 plugged in or twisted type receptacles. Neiman has tons and tons of receptacles that goes from 15 amp single phase 120 into 100 amp 482 73 phase. So most of us guys think of receptacles are these little ones. As we move forward, you're going to understand there are 3-phase receptacles too. Any question guys about receptacle outlet? An outlet that end up in a receptacle, or a receptacle at the end of that, inside that outlet. How about a lighting receptacle? What's a lighting receptacle? Outlet. Write this right above your head. That's called a lighting outlet. An outlet that you end up with light at the end of it, either plugged in or hardwired into it. Any question guys about these terminology? Device, these are all devices right here. Outlets, all these are outlets. Receptacle outlets. Right above your head is lighting outlets. So, comments, questions guys? Any comments, any questions? When we do residential, we have non-metallic boxes most of the time. This looks like a metallic box. Non-metallic boxes most of the time. And now this is not, you guys are not electricians, but if you're an electrical project manager, the first thing you're going to do there and is you don't want to waste copper because copper is expensive. So that's when you get into that rule of 6 from the point that you enter here to this point. You don't want more than 6 inches. You have to have at least 6 inches. You can have 100 feet of wire, but at least 6 inches. And from the point that entered from the edge of the box all the way to here, at least 3 inches. Anybody can tell me why this deal is big deal in the code when we test people? Convenience and termination. When you're going to land these receptacles on terminals, you're going to be able to land them on terminals. Who cares? You guys are designers, right? When you become a project manager, these are the things you're going to watch. Because if you leave a couple of feet here, I bet you your boss will be yelling at you because you're wasting copper. So, right? You don't want to waste. You did?
Yeah.
Old houses, you know, they pulled up all the slack. So a lot of time, if you go into them, you try to pull out an outlet from houses in the 30s and 40s, and you get about this much of your receptacle out of the box.
Yeah.
Because they wired everything and they pull up the slack.
Yeah, yeah. Sweet stuff. And now this is the code. If the code allows 6 inches, it's really a good idea, guys, to go a little bit higher than that. Like you said, 8 inches, 10 inches is not bad. Just to allow you for future, because guess what? You put your receptacle here, you have a short, you burn a little bit of the insulation, you cut it, you push it. Remember, you are designing a system for 50 years, right? Keep in mind that 50 years of the poor people who are going to maintain this system. Okay, so you guys are familiar with that one. Opening, a general idea, it's used a lot overseas. Opening is basically a place where you can put a box or a light. So it's just an opening in the wall. Looks like this. Here's your opening, or it could be like this. So it could be a lighting outlet, it could be a receptacle outlet, a junction box, or other enclosures. A lot of people, anybody have ever estimated based on openings?
Yeah.
So some people estimated based on openings. So consider every receptacle an opening, every switch an opening, every area, and then multiply them by 30 or whatever, $40, and that will get you your bid for that particular job. Obviously, you can't bid a hospital like this. That would be residential, might give you a good idea, but you bid a hospital, commercial building, small stuff, it comes really handy. Okay, so you're going to hear an opening. Another term that they use, an opening, where you put a receptacle or a light or a gearbox. Lumineers. Lumineers, guys, is a sexy term that they use for a fixture, a lighting fixture. A lighting fixture, as you guys, we're gonna study this in details in 6 weeks. A lighting fixture will have the frame that houses so you have to have the frame itself. Inside it, you're gonna have reflectors. A lot of them have reflectors. Inside the reflectors, you're gonna have the lamps. You're going to have a junction box where you tie electricity. You're going to have a ballast if it's ballasted lighting fixture. So a whole lot of things into this piece of equipment. So that's where lighting fixture, complete lighting unit consists of the following. As you can see, you're going to have your lamps, parts to position and direct the light, a place where you can connect to the lighting fixture. And I'm going to spare you the hassle because next quarter we're going to study these in details in the commercial. Outlet location, the amount of light and the type of illumination you need. When we talk about lighting fixtures, guys, it's all about illumination. Typically, here's what typically we do in a dwelling. If you walk into a dwelling, typically you need by code at least one light in every habitable area. Done. That's the minimum. Now, you're going to see, we're going to go a little bit more than the minimum. We're going to put cans to make things look good. We're going to put fans and so forth. But typically, to meet code, all what you need, you're going to have one in every habitable area. You're going to put a light, a switch light, wall-mounted switch light in certain application, or even fixture switch light in other applications. Any comments, guys, about luminaires that you're going to be using? Lumineers. Lumineers. That's a couple of things. Boxes. This article, guys, and I know you went there, and we'll go there in a second, talks a lot about boxes. There are two types of boxes, Jamie, my friend. Box number one is device boxes, J boxes. Box number two is pole boxes. Pole boxes, if you bring number 4 or larger, you bring conductor number 4 or larger into a box, that box becomes a pole box, and the size is completely different. Did you guys do pole box sizing? You didn't do pole box sizing. We'll refer the pole box sizing into where it fits, which are commercial industrial. Now, J boxes and device boxes are a piece of cake. We'll tell you a couple of things about these. There's a couple of articles in any secret book that you know everything. Why do we put devices in boxes? Anybody knows why can't we just terminate like they used to do in the past without a box? Fire. The whole idea of putting a box here, when you put your receptacle, you put your devices. If the devices arc, which it will over time, it malfunction and create a tiny little arc, a tiny little fire. The fire will be contained inside the box, so it would not spread to the surrounding and burn the building. That's the reason why we put boxes. Bearing in mind this errand, that's why the boxes have to be tight. They have to be firmly secured to the location where they're in. So you understand why they put a box. You can't have the box loose there, right? They have to be tight, mounted firmly, and so forth. So that's 300.15 where you need the boxes. Mounting boxes. Okay, so we talked about boxes, guys. Boxes, they can be metallic. Now you talk about here industrial, commercial. Non-metallic, typically residential. So we're right in here, non-metallic boxes. You're familiar with that one. That's most of what we're going to be doing. Metallic mainly is going to be in industrial. There's a couple of things. Boxes also, a couple of boxes, guys, you're going to be doing. Why do we care about this one? Since you're designers, you guys are going to be doing estimating, takeoff. You're going to be doing takeoff. So boxes you can gang, metallic boxes. They can come in different sizes. So you can have 4 gang box. We can put four devices, single gang, 2 gang, 3 gang, or 4 gang box, metallic. Or you can have non-metallic. You can gang them 10 almost if it's metallic. When you mount the boxes, there's 2 rules, guys, very important. Rule number 1, if the walls are combustible walls, like wood, then you flush these boxes, right? You see them flush the box. That's in the journeyman exam. You flush your box if it's combustible. Non-combustible, like walls like these, concrete, they allow you not more than a quarter back from the surface. You can sit it back no more than a quarter. Because it's non-combustible. If it's something is to sneak, it's not going to burn a concrete wall as easy as burning a wood wall. So keep this in mind. Who cares? Since you guys are designers, it's great when you're a project manager to know all this one. Wouldn't it be really great to do to look at all your project, guys, and estimate your project and check your work before the inspector walks in and pinpoint you for you? So knowing all this, The sit back is a good idea. Why? Because we're going to be inspecting your own work. Any comments, guys, about sitting back the boxes? Flush with combustible, sit back no more than a quarter if it's non-combustible. All boxes must be accessible. Must be accessible. When you put a box, you must be accessible. So remember, Jamie, my friend, you put a box, you go sheetrock over that box. If it's a J box or a device box, it has to be accessible. So the reason why you can't pull out of the cover of a box this way and it's violation is because you need to be able to, how are you going to access the wiring inside the box? By the way, from my own experience and from a lot of people's experience, most of the problems when you maintain an electrical box is right to determination. It's highly unlikely that something will happen to that wire inside that conduit. I mean, unless you drill right through it, that could live forever, that wire. It's highly likely that inside the box here, as you pull power and you start putting, say, in this case, 20 amps, and you pull the 20 amps for a couple of hours, then you turn it off. What's going to happen to the termination? Very hot, cold, hot, cold. Hot, cold, what's going to happen to your termination, guys? Hot, cold. Eventually, it will loosen up. And when it loosens, it arcs. When it arcs, it creates a little bit of fire. Hopefully, it will short and the circuit breaker will trip. So most of your problem is in J boxes and device boxes if you're troubleshooting. Most of your problems. That's why the code always requires to have access to these devices, not because they want to bother you. So a case like this would not meet the code in terms of access. How do you do it? You put an extension cord. You guys are electrician. What they do is they have an extension ring, and you pull your conduit. Wiring methods. Therein, my friend, when you guys get into the wiring methods, you did with us. You guys wired with NM cable, right? Did you use MC cable? The ones who were with us, MC. A little bit of MC. There are close to 50 ways of wiring one thing, depending on what type of cable, what type of conduit, a mixture of flexible, non-flexible conduits you're going to see. So a good engineer, a good designer will choose the right wiring methods for the right application. So for example, I can't wire Dunwoody with this because the code does not allow me to use Romex at Dunwoody. But believe it or not, actually allows you to use Romex to wire this room. You know what you need to do? Just put it inside an EMT conduit. Now, who on his right mind will put a Romex inside an EMT conduit just to wire a room like this? So these, when you get into the code, and when can we use, when it comes to residential, the wiring method of choice in most of the applications is Romex like these. Here's another place where we meet the code. Anybody knows why we meet the code with the cable here? Because the cable is flexible. When I unscrew this one, I can get access to this equipment. So that's, keep in mind, it's not a good way to wire it this way. The best way to wire it is to come with an extension cord. But this will meet because it's flexibility. You can unscrew this, move this one down, get access to your terminals. Remember, you need to have access to the wires, to the connectors, your connectors. So can you guys see that this is all, the code requirement that you need? And as you move on, you're going to learn a lot about this system. There's two concepts called bonding and grounding. Very simple, though complicated to a lot of people. I always say, guys, and I've been doing it for a while, I always say, in order for the electrical system to work, all what you need is just one wire. And you go to your basement, Jamie, or anywhere else and try it. All what you need for a system to work is one wire. Take a hot conductor from 120 to 240 panel and pull it, say, 50 feet into your backyard and put it in one side at one side of the lamp, right? Lamp socket. From the other side, drive a little rod into the ground and tie it to the ground, and the lamp will give you light. For electricity to work, you only need one wire, the hot wire. Now, for the electricity to work efficient, you need the second wire, right? So you got your hot, you grab the hot from a 15 amp, you land it onto one side of the light. From the other side, you drag it and you bring it to Mother Earth. That will work, right? Now, that's for the system to work. To work efficient, the smarter than Chad said, now we're going to bring back the return, we're going to bring it back to here and put it at a neutral. So now that's where you got your second one, the neutral. Now, to work efficient and safe, and safe. The smarter than Chad said, okay, let's go grab that ground instead of going to the ground here. And the frame of this box, we're going to take it from here and take it to another terminal that's called ground. And that's how you get your single phase system. Hot to make the system work, neutral to make it work efficient, and ground to make it work safe. Does that make sense? In a single phase system. In a three-phase system, all what you need for the system to work three-phase is just 3 wires. Because three-phase does not need a return, does not need Mother Earth to return it. Three-phase. Why do we pull a ground with the three-phase? Safety. Any comments, guys? Any questions about that? Okay, so we get into two different terms. One is called grounding and one is called bonding. Grounding is that conductor that I pulled all the way to the ground terminal is called equipment grounding conductor. The main reason why having an equipment grounding conductor is if you have accidentally the hot touched the fridge frame, for example. Now you have a frame of a fridge that's hot, energized. Now, if the frame is not grounded to the ground slot, the voltage will be sitting there for you to grab into the handle of the fridge and goes right through you, especially if you're barefoot in the basement where your beer is, and it goes right through you and burn you, basically. So that's where we got the ground. Now, if it's grounded, you're going to have short circuit, ground fault, what they call ground fault, hot to the ground, and that will facilitate the operation of Mr. Protector here called circuit breaker, and it will trip the circuit breaker almost instantly. So that's where the ground is. Facilitate the operation of the circuit breakers for residential or commercial or industrial. Everybody's okay with that one? So that's why we ground the system. Every system you have to have an equipment ground conductor within every system, with very, very limited application. Now bonding, the way we bond things that's electrical or things that's non-electrical that could be energized. A tank. Suppose that you have a tank that's sitting right here, and right next, this is a tank, that's nothing to do with electrical, and right next to it is some pump here. And at one point, that tank could be energized, right? So what we do is we grab a wire here, and we take the wire to the ground to bond that tank. Water heaters, we bond water heaters. All the stuff that we have, we bond it. Why? Because we don't want these non-electrical equipments to get energized, number one, and hurt somebody. And number two, we don't want them also to get energized and have a difference in potential between them and another object. So if you have two metallic objects, guys, one of them sitting at 50 volt, the other one is sitting at 0 volt. Now you have a voltage difference between them. If I grab in one hand on that object, in the other hand, the other object, you're going to have a current going right through you. So that's where the bonding is. You bond things to make sure they're always sitting at the same potential. They call it the same voltage, the same potential. So that's the equipment. We ground equipment ground conductor to facilitate the operation of the overconduction device. Bonding is to put everything at the same equipotential. We'll talk about this one in details as we go into the commercial and industrial. Just keep this in mind while we bond. Okay, so we're moving. This is a couple of things. We'll talk about bonding and grounding for dwelling, guys, as we move on. Back into the boxes and devices. Almost all your boxes they're going to be using in a dwelling is non-metallic. Why do we use this one? Economical. It's easy, cheap, and the wiring by a number of specific circuit. And we'll talk about the specific circuit that we wire a house as we move on. I will review, guys, with you tomorrow or Monday all the rules for dwelling. The code is so intensive when it comes to dwelling. Anybody knows why? Because people like to work on their homes, so they're very specific. I would, if I'm to dare to say something, if 100%, if the code is 100% clear about residential, if you move it to commercial industrial, it's 50% clear. Why? Commercial industrial is the public. It's not exposed to the public. You and I, not my children. You know what I mean? For the most part. And people don't work on commercial industrial, non-qualified people. It's supposed to be qualified people. So, okay, boxes, non-metallic for these. We talked about multiple gang, guys, boxes. And we talked about 2 to 3 to 4 gang, especially up to 4 gang boxes, non-metallic, that you can put. And for box fill calculation, The non-metallic is always have the cubic inch volume is marked inside the box, as well as the number of conductors, typical conductors that we use, 14.2, 12.2, 14.3. They tell you 3 of this, 2 of this, 1 of that, a mixture of all of the above right inside the box. Non-metallic boxes, they are not, and we have tables that we do the calculation based on these tables. Any comment, guys, about gang switches and boxes for dwellings? We'll talk about non-dwelling as we move on. This is for your dwelling. So the whole box, we talked about why do we need boxes. This is really the key word for why do we need box right in here. Why do we need box for all these devices? Spread of fire. We want to minimize the spread of fire upon the existence of a ground fault or a short circuit or an arc flash inside this box. Really no big deal. Closing all the gaps. When you have any gaps between the box, and we're going to close it because of what? Spread of fire. It's all about the fire, spread of fire. Otherwise, do you guys see the electrical utilities put boxes up in the air for their transmission distribution system? Do they put boxes there? Have you ever seen them put a box when they do it, when you tap from these conductors? They don't box them. Why? Where is the power? Where is it going to spread? If there's a fire up in the air, where is it going to spread? It's going to sit there and extinguish itself. So you put it in a building. That's why the NEC code book is mainly for indoor buildings. A lot of stuff indoor building. You go outdoor, they're so relaxed. I can go done with it right now on poles and tab from pole to pole with no box and keep moving. As I'm outside the box, outside the building. There's a couple of requirements, guys. You have to maintain 1/4 of an inch. As you will talk about this one as we go. When you put your boxes, you have to maintain 1/4 of an inch when you drill your, from the place where your nails are going to be located, so you don't bust right through the cables. When we do remodeling, obviously you guys are not doing design remodeling, but when you do remodeling, a couple of things for remodeling. You draw a hole. Before you draw a hole and put a box, what would you do, Jeremy? Make sure you can get access to it. The worst thing they could do is you drill a hole and you put a hole for your box without knowing that you can fish the cable into this location. First of all, plan your route, then you put your box. Madison Holdens, you guys are familiar with these. These are very common for remodeling. Who cares, you being designers, since, well, you're going to be working on probably your own homes. Other than that, if you're a project manager and you have an apartment building and you guys, they hired you and your firm to upgrade the system to code, and you don't want to bust through the walls, be aware that there's something called remodeling devices that you can use. One of them is these Madison holders. You put the box, and you guys, did you use them with Gary? And you can bend them, and that will hold your box inside the cavity of the wall. Okay, everybody knows why we have the boxes, because we don't want to spread to protect lives and properties from the spread of fire. That's why the whole idea of the boxes. Building codes also, we know what the NEC code says, put them in a box. Also, building code have to be followed, guys. Building code has to be followed. Based on the building code, and that's also enforced, is you can't, in a fire-rated wall, you can't put them back to back in a fire-rated wall. For example, in dwelling, the wall between you and attached garage is a fire-rated wall, double sheetrock. Why? Because there could be a fire generated by your vehicle. So if it's attached to garage, fire-rated wall. So in the cavity between your garage and the house, that one you can't put two devices in the same cavity. You have to put them into two different cavities, or you have to put mud. You have to put some type of insulation around it. So you have to have some insulation that maintain the integrity of the fire-rated wall. There's a couple of nice pictures I'll show you. There you go. So if this is a fire-rated wall, 1 hour fire-rated wall. Now, Jeff, would be between you and detached garage, attached garage. So they don't allow you to put it this way. Why? Because if there's a fire here, it goes right through this box and into the other. You compromise the integrity of that fire rated wall. So what do you need to do? You can put them in two cavities, then this here is closed, so the fire will stop, hopefully will stop right in here. Um, or I think there's another picture where you can put wrap the box with a fire rating that maintain the integrity. So you can wrap the box, one of them here with a wrap, you'll see there's a nice picture of that, wrap that box. That's only for fire rated walls. The inside walls of a building are not fire rated walls, the dwelling. Typically that will be in between you and attached garage, typically. In a commercial building, there's a lot of fire rated walls. A fire rated wall will go from here all the way to the structural ceiling. If you want to know if it's fire rated wall, if you stick your head at the top and you can see the other side, that's not a fire rated wall. It goes all the way to the structural ceiling to limit the spread of the fire in one, confine the spread of fire in one area. Okay, so be aware that you can't put them side by side, but remember, this is not in the cavity between the bedroom and the hallway. We're not talking about this one. That's between a garage and the house, attached garage. We talked about the no gap. Because of the spread of fire, guys, you don't want to have a gap less than requires there will be no gap or open space greater than 1/8 in at the edge of the box or and the fittings or the fittings. Again, it's all about the spread of fire, so you're going to close all these. I think in Chicago and other places where they require you to use conduits instead of boxes, if you are to use and basements, if you have basements, you can.
You know what that anyways, with Conduit in Chicago or whatever that's called.
Are the conduits more safe than a NAM cable? Absolutely. You know, I can easily drill a hole. Remember, dwelling. People are drilling holes in the walls all the time. Ladies and men and qualified, non-qualified people. You can easily drill right through this. We maintain 1.25 inches. Usually you have to put 1.25 inches, but that's just 1.25 inches. People have a bigger screw can go right through this 1.25 inches that we maintain in the middle of it. So now if you put an EMP conduit in these walls, it's highly unlikely they can drill. It's just more safe. Is it more safe? Yes, but a little bit overkilling.
Well, because it's like, why do they do it but we don't?
It's I guess based on this is America. They have decentralized government. Every government can decide what's safe and what's not safe. Why does Wisconsin still use 2008 and we use 2011? So it's the judgment of the professionals in this area. We tend to be strict, but Chicago tends to be more strict. Maybe the people there are rougher than we are. I don't know, but yes, sir. The what? They have their own code too. But again, the NEC, guys, is a bare minimum. The NEC is allow you. Everybody knows how the NEC is adopted by the state of the or the city. What the NEC allow? What happened if I don't want to adopt the NEC? Anybody knows what happened? I decided the city of Bloomington throw the NEC, and now we're going to wire our own. If I don't have my own code is as strict as the NEC, if not more, then not a single company will insure my buildings. You get into insurance. So you can do anything you want as a local government, but there's consequences. What's the consequences? Or your insurance in that area will be double, triple. And then the government will not be elected next time, right? So there's consequences for the decisions that we make. So that's why this becomes the law by default. If you can, this is accepted by the insurance companies. If you meet the NEC code, you meet the minimum requirement for safety. You don't meet it, then you have two ways. Either you have to have something as strict, if not more strict, or you are risking that your building will not be insured, or if it's insured, it's going to be very expensive to insure it. So, and it might be at that time when I don't know really what's the philosophy behind it.
What about like Wisconsin, where you don't even need to have inspections if you're in like the smaller towns and villages and stuff like that?
They're changing it to a statewide licensure and inspection now.
Yeah.
What is it? 2013, I think it's going to be. Okay, not just to stop your guys' good discussion, but a couple of, if you were to use wiring, typically a square box is 4-inch square box with plaster ring is a big deal that they use in dwelling or non-dwelling. If you were to use the conduit, Yokes. We talk about yokes, guys. These are called yokes. This is a 2-device yoke, right? 2-device yoke. You can have a 1-device yoke, a 3-device yoke. This one happened to be a 1-device yoke. We'll not use it here. 1-device yoke. You can have 3-device yokes. Attached to they attached them with this size of a screw, 632. Just a couple of things about the devices. Special outlets. There's special outlets, guys. We use the most common outlet, convenient outlet that we use in the US is 15 and 20 amp. Everything is 15 and 20 amp, typically. 15 and 20 amp, 120. These are 90% of your typical outlets. There are other outlets that goes 20 amp, 240, 30 amp, 240, 40 amp, 240, 50 amp, 240. These are special outlets. We'll talk about them. Notoriously famous 30 amp for your dryer, electric dryer. 40 amps, 40 or 50 amps for range that we use. 30 amps. So these are the two notoriously famous that you can use in dwelling units: the dryer and the range. 30 and 40 amp, 240 receptacles. These are what we call them in the code special receptacles. We give them special symbols. You're going to see when we do that, when we put them on our plan. So it's going to look something like this symbol or something similar, or a special receptacle. You're going to show them. We have a symbols that we use, guys, for special receptacles. What I would like you to do, Jeremy, my friend, when we have a range, because we have a range, when it comes to the range, don't use the symbol for the duplex receptacle. There are a special receptacle. That's all. Then you specify the voltage and the amp right onto it. Okay. 314.16a and b, guys, these are notoriously famous places where we can size how many conductors can fit into a box. How many conductors can fit into a box? I'll show you a couple of things. 314.16, I'll show you this table. Will give you how many conductors can fit into a box and how do you do a box calculation. 314.16b will tell you what's the cubic inch allowance for a conductor. Coming in a second here. Okay, now when you select conductors, I'm going to go right into a nice. This is just a couple of things about selecting conductors, guys. Let me give you a 5 minutes break because I want your full undivided attention, and we're going to do just one example about box fill calculation because you guys have done a lot of them, and emphasize a little bit about these two tables. Shall we have 5 minutes break? And then we'll guys jump in here, get you your full, then I can get you your full undivided attention. We talked about this one, guys, layout. Okay, so we talked about the outlets. This is a lighting outlet. Just a couple of pictures to emphasize the lighting outlet. Can you guys see that all the termination into a box? So there's no spread of fire. Just a picture of lighting outlet. A couple of symbols. This is the symbols that we use. I gave you guys yesterday. We loaded symbols right there, tons of them. Our palettes. They're very similar to this. You're looking at the duplex receptacle, which is right in my hand right here, 20 amp or 15 amp, and you're looking at three-way switches and a ceiling lighting outlet. These are symbols for these. You don't have to memorize them, obviously, because they change. Here's a couple of set of symbols that we use with this in this project, guys. Look at the ceiling on the wall. The reason why I don't want you to memorize or do anything else, because we have already our symbols. Just keep this in mind as a guide as we move through. Surface mounted incandescent lamps. Look at the symbols that they use. Look at the walls, how they have that little dash at the end. We have the pull switch, lamp holder with a pull switch, that little chain that you pull it. Typically, these are residential. You don't do a whole lot of commercial with it. Look at the incandescent lamps, recessed ones, how we symbols for them. Surface mounted a fluorescent, recessed fluorescent, surface mounted continuous rows, and so forth. So these are just, please, as we go through this year, guys, please keep these in mind when you look at a symbol and you have no idea how it means. Please look at these. These are guide plus the stuff that we gave you guys, the symbol legend that we have. Blank outlet, junction boxes, and so forth. Any comments, guys, about these? These are just FYI inside your book. If you move to the second one, these are typical outlets that we use. I want to emphasize single. Can you guys see my single receptacle outlets, duplicate receptacle? This guy, a special receptacle, D dryer, that's typically 30 amps. Duplicate receptacle outlets, split wired. You guys split circuit receptacle where you can have the top on one circuit, the bottom top on one circuit, the bottom one circuit, and you split the connection between them on the hot side. You guys are familiar with that one? All the clock outlet and so forth. Again, these are just FYI, so please keep in mind, this is going to be a very big deal when we go into the commercial. The double duplex or quadruplex. Quadruplex, we're going to use a lot of these quadruplex into the commercial industrial. So pay a little bit of attention to this boy here. Waterproof receptacles. So these are, again, a couple of receptacles. GFCI, we have two symbols to do GFCI. Range, if you have a range. This one is special purpose receptacle for dishwashers and so forth. So any comments, guys, any questions about these symbols? So please look at them once in your life as we start designing this project. So that's kind of a couple of things I would like you guys to look at. Switches, look at all the combo of the switches that you can use. Everybody's familiar with a single pole switch. How about double pole switch? You're taking two hots. We're doing residential now, not three-phase. Two hots, and if you're turning on the two hots at the same time. Three-way switch. Three-way switch is the only location for a three-way switch, as we all know. If you want to turn a light from at least two locations, you need three-way switches, right? Four-way switches, if you want to turn the light from at least three locations, right? You have a three-way switch in between, a four-way switch. Three-way and four-way are used to allow you to control a lighting fixture or an outlet from multiple locations mechanically. When we go to the commercial industry, you're going to forget about this. We have relays and we have low voltage system, and that you can control with a relay. I can control all the lights are done with it from one single outlet. Push a button and you can turn, or from my computer. So all these becomes obsolete, guys, as you move into the commercial industrial. Door switch, like the refrigerator. When you open your refrigerator, like a closet, they use them a lot in closets. If you want to open your closet, the minute they open the door of your closet, the light will come on. So there is a jam switch. It's jammed. Normally open, held shut. Normally closed, held open. Contact. And when you open, you release the pressure on it turns the light on. So dimmer switches, glow switches, the ones that glow, keyed switches, all these, what I want you guys to look at them when you start throwing your switches and you want to guide, when you use special switch, look at these. Low voltage master switch. The master switch, we use it in a commercial project later on. That guy, you flip it, the secretary at the end of it, she flips it, he or she will flip it, and it will turn all that off. Master switch. Occupancy sensors, look at the that we do occupancy sensor sealing. We're not using a whole lot of occupancy sensors. Timer switch, variable speed switch, weatherproof switch. This is variable speed probably for fans and so forth. So these are all a sample of ANSI type, ANSI, American National Standard Institute symbols that you can use. Can you guys use them in the back of your mind in conjunction with the symbol list that I gave you yesterday in our project? Can I have thumbs up, Chad? We got that one? Okay, thank you. So keep them in mind. You don't have to memorize them. Circuits. When it comes to the circuit, guys, here's a couple of things that you can do about circuits. Branch circuit home runs. Always when we do a home runs, we have to specify. You can see the arrow where the home runs is done, and we have to specify A-1, 2. This is circuit 1, 2 coming from circuit A, if I remember right. home run to the panel. Number of arrows indicate number of circuits. We have 2 circuits here. Letters and numbers indicate circuits. 2 circuits going. Full slashes indicate ungrounded conductor. Half slashes indicated. This is a multi-conductor circuit. So you're looking here basically in a circuit here, 2 hots and a neutral. 2 hots and a neutral, right? Multi-conductor circuit. And don't forget the ground. Here's my ground, always the ground. Here's hot 1, hot 2, and the neutral. That's what basically you're looking at. The symbol that I use, guys, slightly different in our project, you're going to see, but it has the same meaning. When you have a home run, you need to indicate how many circuits you have in the home run, 1, 2, or 3. You also need to indicate how many wires going to the home run. Is it at least you need to have 2 wires and a ground, right? At least a hot and a neutral and a ground, right? At least. Now sometimes you group multiple circuits in a multi-wire bearing circuit. Then you had another hot, so that would become 2 hots, neutral, and a ground. That's called multi-wire bearing circuit. That's what you're looking at. So keep this in mind. Again, we're using slightly different configuration. Okay. And so branch circuit, full slashes, and so these are, and I don't want to go over them because we're using slightly different than that. Wiring concealed, look at the symbol for wiring concealed. Conduit concealed. Conduit, look at this one here. Conduit up, conduit down. Can you see the dotted here? Conduit up, conduit down. Okay, let me see if I can cut that boy here. Move it away from me. Okay, so that's a couple of things. Conduit only, empty. This is the one I would like to pay attention to. Switch leg, that loop. So please pay a little bit of attention as we move through with these circuiting. We have our own slightly circuiting different in the project that we do, slightly, not a whole lot. But please be aware of that, especially the conduit up and down, the symbols that they use here. We're not using a whole lot of conduits in the project that we do. Okay. Let's get it out of here, out of way, huh? Low voltage. And there's a couple of things, a couple of outlets and things that you can look at too. Let's look at something really interesting. Look at the circuit breaker, the buzzer, the batteries. And again, these are all junction boxes in the ceiling and the wall. Lighting or power panel. Look at the power panel, lighting panel that we use, motors. Low voltage. Look at the telephone and telephone data. This outlet here, can you guys see that one? We use it all the time. Data outlet, especially in the commercial. So when you guys going to be doing, for me, every time now with this internet, I know there's wireless now. Wireless, and who is going to do it? Chad. So I like to use this one all the time in my plans and wired, but you know, everything is going wireless now. It's interesting. Fans, look at the fan, ceiling mounted fans, and so forth. Can I get you guys to, huh? Cat 5. That's that particular one here, data. Yep, that's you. If you put this one on the plan, this means you're bringing a 22 a phone line and a Cat 5 into this box. But again, with the wireless, it's becoming kind of an interesting right now. But when I told you guys in my project, I still want the house to be wired with Cat 5. So you're going to bring a symbol like this for me later on and throw it. This will indicate there will be a home run Cat 5 into the hub here.
Is the commercial stuff going to wireless too? Crazy amount of wireless.
Yeah. There's a lot of, like here, we're done with it. We got almost wireless. I remember when I started here, all these will be wired and you plug in yourself. So they bring the router to here. These are the old routers we don't use a whole lot. But we're going to wireless. A lot of people are going to wireless still. But wireless doesn't mean Cat 5 is going to go away, guys. Because you still have to bring Cat 5 and you know, and fiber optic cable into a certain location and then spread the signal to that location.
Wired is still more reliable anyway. So it's nice to have that though.
Yeah. So we still have a lot of, here, then we still have a lot of stuff. So that would be a good question when we do the commercial to, we still put conduits. When we design project conduits for low voltage and boxes and so forth. Okay, notification, guys. You're gonna do a little bit of symbols for notification. So if you please pay attention to this one. For example, look at number one. If you put that one next to the symbol, it says plug mold entire length of the workbench outlet 18 inches on center install 48 inches to center from the floor GFCI protected. So if you have like the mold in front of you, if you want to specify what type of mold you need a GFCI protection and how many of these, that would be a really nice little circle with a number inside it. And right next to it will keynotes, like keynote. These are your keynotes, and you indicate what you want. We put these one next to things that could be confusing. For example, I put a receptacle right at the top for my plasma TV. I have you keynote this receptacle and say mount, I don't know, 5 feet on center. Was it above finished floor? So they have a lot of notification that you do. So please pay attention to that one too. We talked about split circuit guys receptacles. When you have a split circuit receptacle, circuit 1 top, circuit 2 bottom, weatherproof receptacle outside, WP weatherproof. Here's a couple of circuits and boxes that you can use, and I'm going to cruise through these guys because you are familiar with that. So please just look at them. I don't know how many of you guys have seen this outlet. Look at that little special outlet, three receptacles in one yoke. So a couple of devices. This just will show you guys the device, the actual wiring circuit. If you're not familiar, Aaron or anybody else guys, with the actual wiring, this is really nice because it takes the single switch and it shows you how the actual physical it looks like, how symbols that we do, and in operation on off, and how you wire it in a circuit. Please look at these if you're not good with wiring. This is really cool. Look at 3-way switch and 4-way switch. It shows you actual wiring for 3 and 4-way switches. And I know a lot of you guys probably know how to do it. But if you don't know, don't leave Dunwoody without knowing how to wire these. So if you want me, we can go to the lab, we'll wire all these, not really rocket science. Yeah, absolutely. So that's not a biggie. Connections, terminations. Sometimes we transfer from one wire methods to another. So this is taking you EMT to AC. That's where a project manager becomes really big guy. So you're going with MC and I need 2 ways. If I want to go to AC to EMT, the easiest way is to put a box like this, right? And transfer. There's also a fitting that can take you directly from one wiring method to another. So just be aware. This is good for a project manager, guys, to know that one. Number of boxes. We talked about these different boxes that you can use. Here's all the single gang, 2 gang, 2 gang, 3 gang, and 4, 1, 2, 3, 4, 4 gang devices. Everybody's familiar with that, I assume? Cool. So be aware of that one too. This is the sizes that you can do and how many conductors you can put into them for boxes generally used. Look at this one, how many conductors. Number 14, I can put 3. Number 12, size 12, I can put 3. So this table is really nice. It tells you how many conductors you can bring to the box, but only conductors only. So it doesn't talk about the devices and so forth. So look at these. It's really not, again, nice to know. Let's go to devices, boxes, mounting. There's a lot of hardware, guys, you can use when you mount receptacles. If it's right next to the start piece of cake, you nail it to the start and move on, right? If you put it right in the middle, a fan in the bathroom or a light or something, you have to have the special hardware mounting strips like these that you can mount your equipments to. Remodeling, you guys have seen these for remodeling where you put a box, ceiling box, couple of remodeling stuff. We talked about fire rated walls, and you can't put them back to back. You have to put them in 2 different cavities. You can put them back to back if you have look at the divider in between them. So please look at these pictures. They're really cool installation, only if you're becoming project manager, or you can put all this stuff around it here, the fire resistance, but you still can't put them back to back like we were just talking here. And you can put 2 boxes in the same cavity, but they have to be rated as fire rated boxes, and you maintain the 3-inch between them. So these are really this is the material that you put on around the box to make a fire rated box. Mud rings. Okay, so that's basically bringing us, guys, into the boxes, the box fill. You're familiar with the box fill calculation. This is a really nice example that they have in the book for you. If you have a 4-inch box, it's 4-inch box, and it's 1.5-inch lead. If you go to table 314 dot 314 dot what? 314.16, it will give you a 21.21 inches. If you put a mud ring around it, like this one, that will give you this amount of inches, 4.5 cubic inches. The total will, here's your total now, right? So you put a box, you put the ring on it, and together they give you 25.5 cubic inches. Cool? I'll tell you where to get this information from. Just add them up. Then if I want to find how many conductors, number 12, I can bring to this box. Here's the cubic inch, how much I can fill inside this box, right? With the ring. That's how much I can fill inside this box legally. Each conductor, number 12, is assigned by code 2.25 cubic inches, by code. This is from table, you're going to see it, 314.16. So this is how much I can fill, and this is how much each one of them can take. If I can take the cubic inches of every conductor, divide the available space by that cubic inch, I can find how many conductors I can put in this box, just conductors. And that will give you 11 conductors, number 12. So that's just a simple calculation that we use for box fill calculation. Talk about this one. Okay. Okay, we'll talk about a couple of things, guys. Let me just erase that one and go. I'll get back to the calculation in a second here. Believe it or not, the way we put the receptacle here says it's not recommended. This is typically a lot of homes here in Minnesota is put the receptacle. This is orientation of the receptacle in the box. How do you orient the receptacle in the box? This way, or that way. So this one is not, again, not code though, recommendation. Look at the recommendation. Here's what's recommended, to put it upside down. Anybody likes it this way? A lot of us here, at least in Minnesota.
Anybody really does that around here.
Yeah, it's unreal. I mean, the different parts of the country do it differently. The idea, guys, here's what the argument over it. If you mount it this way and a sharp object is to fall up, right, the first conductor is to be cut is the grounded conductor, not the hot. So, right, because you hit the ground here, that's a grounded conductor, so you're not going to short, basically. If you do it this way, right, and you sharp object falls, it's going to cut right through that little slot. That's the hot conductor slot. So you're going to short and create a fire. I don't know. So what do? Yes, sir.
But if you like, I mean, a lot of plugs come out of the wall where they're kind of like coming out of the wall and they'll lean, down. So wouldn't you want the grounded conductor to be the last thing to come out of the wall as it falls out?
That's by design, though. They design them a little bit longer. See how
But
they
if it was to
design.
fall out this way, it'd be the first thing to come out of the wall. So wouldn't you want it to be
Yeah,
last
yeah.
thing to come out of the
I hear you. I hear you. I hear you.
Metal already, man.
I hear you.
It cuts the ground first instead of.
It cuts the ground. So anyway, this is, I don't even pay attention. This is based on the book, not recommendation. Here's a recommended part. Can you guys see why it's recommended part? Because again, that sharp object is going to cut right through this. Everybody knows that this is the neutral and this little slot is the hot. So if you put it this way, always you're cutting through a grounded conductor, not the hot. You're avoiding to cut through the hot. Cool? So that's another recommendation. Why this is, anybody can tell me why, based on at least their idea, why this is not recommended? Just look where the hot is located. Yeah. So it's, I can't defend it. It's so, just be aware of that one. At least in Minnesota, we mount them upside. I call this is the proper way of mounting it. A lot of us mount them this way. So code-wise, the code care less. The code care less how you mount them. Okay, a couple of things, guys, when you mount your receptacle. This is code. When you want to mount them, look at this one. This location is, anybody can tell why this is not right? Yeah, you can't put it half and half on the tile and half on the sheetrock. So you can either all in the sheetrock or all in the tile, not the. So this is, who cares, project manager? You become a project manager, all these little things make you a good project manager or a bad project manager. Installation. You guys should inspect your work before the inspector walks in, right? Since we're not the installers here. Aligning screws, I don't know. Do you guys do that? Align your screws?
You know, to be honest with you, I never even gave it a second thought until one person said something about it, and now my OCD kicks in, and now they all have to be lined up.
Yeah.
From that
Do you guys see the alignment of the screws here, right here, and right here? It's good workman. Do you guys do it? The good workman-like manner, basically. Workman-like manner. So line them up, they look nicer. Looks that has nail. Okay, we'll get that one. Couple of boxes, couple of hardware. You guys will look at these hardware that you can do. Here's what I would like you guys to wake up here. So let's go back directly to this table. Please, if you want to highlight one little thing for me, look at this table inside your book. Could you please? This will summarize all the conduit, the rules of box fill rules. Okay? Can I get you guys to go to this table? Okay, when we do box fill calculation, as you guys all know, the clamps, all the clamps count as one based on the largest conductor into the box. So if you guys want to highlight one little table that summarizes all the rules of box fill calculation, this table is the table. Cool. So let's just quick look at the first one. First of all, this is coming from 314.16 B1 through B5. If you want to go to the code and refer to it, because that's not the code. Let's look at this. The clamps. All the clamps count as one based on the largest conductor in the box. Number two, support fittings. Add a single volume for each type based on the largest conductor in the box. If you have a stud, one volume based on the largest conductor in the box. Or a hickey, one volume based on the largest conductor in the box. Devices or equipment. If you have a device, you give it 2 volumes based on the conductor landing on that device. If I'm landing 14 here, the 2 volume will be based on 14. If I'm landing 10, the 2 volume will be based on 10. Do you understand? Based on the conductors landing on these terminals of the device. But 2 volumes, double volume they call it. Equipment grounding conductor. All your equipment grounding conductor in the box count as one. Am I speaking a language maybe other than Aaron? Am I speaking a language that everybody understand? All the equipment grounding conductor count as one based on the largest equipment conductor into the box. So number 10, number 10, number 12, number 12. Isolated grounding conductor. You bring an isolated grounding conductor that also count as standalone conductor, right? Typically work for certain application. Look, these are my favorite. Conductors. If you loop the conductors less than 12 inches, you bring here's a box. You pass the conductor right through a box for less than 12 inches, it counts as 1. If you loop it 12 inches or more, it counts as 2. So here's my box. Oops. Here's my box. And if you loop the conductor, this counts as 1 here. If you bring it and you loop it and you go this way, and this is more than 12, this will count as 2 conductor. Why? Because you're planning in the future to chop this baby here, so that becomes a 2 conductor. Every conductor that enters the box count as 1. Cool? Everybody's familiar with that one, guys? Every conductor enter the box count as 1. So I can't emphasize that how important this little table here is when you do your calculation. So let's just keep going through that one. So here's number 12. For conductors that originate outside the box and terminate in the box, you come from the outside in, you count as 1. If you pass through, you count as 1 without a loop. If no parts of the conductor leaves the box, pigtails, all your pigtails that you do in the box, do they count? No, your pigtails don't count. If those of you who wire, guys, you pigtail the hot and then neutral sometimes in the ground, and all these pigtails inside the box don't count. The last one here, for smaller equipment grounding conductor, or not more than 4 conductors smaller than number 14. Smaller than number 14, that's a fixture wire. Number 18 and 16 originate from a luminaire with a canopy, they don't count. So you have a little luminaire with a canopy here, and you have 4 conductors, number 16, coming from the fixture to land into the branch circuit. 4 or more, 4 or less don't count. 5, they all count. Okay. Smaller fittings, wire knots, and so forth does not. Aaron, my friend, if there's anything you want to understand the box fill calculation, that's the table. Summarize the whole deal. Any comments, any questions, guys? So when we say, later on, when we say we have a box and we have a conductor that's passing through the box, it's going to count as 1. If the conductors terminate through the box, count as 1. If the conductor is looped with 12 inches or more, count as 2. A box has a device like this. This device count always as 2. Based on what? Based on the conductor that's landing right into that box. The equivalent grounded conductor count as 1 based on the largest. What else? If we have clamps, all your clamps count as 1 based on the largest. Did we forget anything else? So that's basically summarizing the whole. Yeah, 18 gauge or 16 gauge or less. These are less than 14. 16 gauge or less, up to 4 coming, they don't count. Okay. Any comments about this table? That's summarizing the whole deal that you guys did. Let's go to the second table. Oops, I'm going to go directly. Okay, here's the table that you guys. This is directly from the code. For those of you who haven't used it, this is how we use this table. Suppose that I'm using this box, which is for a square inch. It's 4 by 4 by 1 inch and a quarter, right? This is how we use this table. As a J box, I'm using it right there as a J box, not as an outlet, just a J box, right? And I want to know how many conductors I can bring to this J box. What size conductor, Chad, you're using? I'm using conductor, all of them are number 12. Okay, anybody can tell me all the conductors are number 12 that's coming to my box. How many conductors as a J box I can bring into this box? 8, right? So here's 1, 2, 3, 4. 1, 2, 3, 4. Here's your 8 conductor. If you bring a 9, what happened? You violated the code. That's for the metallic boxes. So let's take another example. Device. Here's another device box. A device box is the one that right here in the wall. You're looking at it. I have a device box. The shallowest box is 1 inch and a quarter device box. And I want to bring this box and use it as like this, a J box here. It's using it as a J box, right? As a J box. Device box, I'm using it as J box. And I decided to use number 14 in it. How many conductors number 14 can I bring in this little guy as a J box? Everybody can see that? 3. Aaron, does it make sense how to use these? So you have to decide what type of box I'm using. A J box? I'm using them as J box. Device boxes or square boxes? Round octagonal boxes. Let me use this one, the last example, 4 by 2.5. And I'm using it as a J box, and I decided to bring number 10 into it. How many conductors number 10 I can put in this baby? 8. Piece of cake, right? Everybody knows how to use that one? That's if they're all conductors. If you have conductors and devices, then you start converting the devices into conductors. So if there was, right, you start converting them devices into conductors. So let's suppose that, let's use this one. I have a device box right here. Take this. Okay? I have a device box, device box, and I only have one device in it. One device, right? And the conductors that's landing on it is number 14. So I have 14, 3. Let's take this one example here with a device. Very quick here. Make it the simple way, right on the calculation on that boy here. And I know some of you guys have done that one, and it's a quick review for those who did not. Here's my device box. I want to use a deep device box right here, the deepest boy. Cool. And this is my device box. Inside the device box, this is for you, Aaron. Inside the device box, I decided to use a yoke. receptacle, right? I can use any receptacle I want. Inside the receptacle, I have the following. I have a clamps right here, and I have a cable coming out of here. Inside the cable, I have a hot and two hots. I have a hot and neutral and a ground, okay, right? Just a receptacle, hot, neutral, and ground. Just box in the receptacle. Cool, everybody's okay with that? And I have a clamps inside it. And I have a device. Okay, so let's see if this, well, let's see what's the shallowest box that I can use for this. The shallowest box. The shallowest box. Okay, how many and all of them are 14. This is 14.2, right? 14.2. We don't count the ground. 14.2. All right, conductor wise, let's use this color. How many conductors do I have? Can you guess conductor number 14? How many? We don't count the ground. 2. I have 2 conductors. All of them are number 14, by the way. Ground. How many grounds do I have? 1 ground. Clamps. How many clamps do I have? I have a clamp right there. I put a clamp. Okay, devices. How many devices do I have? 1 device, but the device always goes by 2 though. They count as 2. As 2. Why did I multiply the device by 2? Because device have 2 allowances. Cool. 1 device, 2 allowances. Okay. And all of them are, do I have other than number 14 conductor? All of them are the same size. So when you add them up, So I have 2, 3, 4, 5, 6. I have 6. So I need to find a conductor, a box that can house 6 conductors equivalent to 6 conductors, number 14. And I need it to be a divide box. Okay, let's go look here. I'm under here. Okay, let's go. Can this box work? The first one. I need 6, remember. Can this one work? Can somebody say no, Chad? No. Can this one work? No. How about this? So what's the shallowest conductor that I can use? All the way to 3 by 2 by 2.5. Aaron, this is for you. Does it make sense? That's it. That's a rocket science about the box spec calculation. If all the conductors are the same, all the conductors. Any questions about this? If there's no devices in the box, it's even easier. You know. Now it gets a little bit complicated, not complicated, more calculation you need if you have different sizes of conductors. And the second thing I want to do is this different size of conductors. Any question guys about this example? Any question about this example? Piece of cake, right? So that's this one. So let's take an example. Before we take the example of, so let's do that one, and then I'll. Okay, here you go. Okay, so before I do the second example, I would like you guys to go to the next table. Next table. This table. This is for my friend Aaron. This table, Aaron, you only use this table if the box has different conductor size. You pay attention to it. If all the conductors are the same size, do we pay attention to this table? Don't even look at it. Does that make sense? Can I have thumbs up? Chad, we understand that we don't even pay attention if the conductors are the same size. Okay, the smarter than Chad took a wire and did the cubic inch calculation on that wire. And they came up with this table. So the most important ones that you guys are going to be using as probably most likely is right in here. For number 14, what do they give it? 2 cubic inches. And 2 1/4, 2 1/2, and 3. These are probably the most important ones. So every time you have a conductor, number 14, you're going to convert this one into a currency of 2 cubic inches. Why? The reason, Aaron, that they do it, guys, and everybody else says, how are you going to add a number 12 with number 14? You can't add them up, right? If I convert number 12 into cubic inches and number 14 into cubic inches, I can add them up now. Does that make sense? I can't add dollars into euros. Can you? $100 with 100 euros is how much? I don't know, Chad. I can convert the euros into dollars. Now we talk, now we understand the value. Does that understand why we have these cubic inches fancy stuff? Okay, keep this in mind, and I want to do an example. Aaron, this is directly for you. Does it make sense why we have this table? Okay, and I'm not picking on you because you didn't do the calculation. Okay, let's go now. Yeah, that's all. Yeah, absolutely, because you haven't done it. Okay, now I'm going to have an example, very quick example here. I have, here's my example. I have a box, a 2-gang box. Okay, a 2-gang box. And inside the 2-gang box, I'm going to have a receptacle and a switch, receptacle. And to add, I want to bring here and here. This is, I want to bring into this one is 14, 2, and this is 12, 2, 14, 2, and 12, 2. The 12, 2 is coming into the receptacle, and the 14, 2 is coming to the switch, right? Makes sense? I want to have also clamps. I want to clamp it, internal clamps. I'm clamping it, so I have clamps. Cool? And now, what's my question is, what's the smallest double gang box? Double gang box. We're going to have 2 gangs now. We're going to gang 2 together. The smallest that I can use. 2 gang box that I can gang them together to get me that a box for these 2. Shall we do the calculation? All right. So let's start here. Right on the right here. Let's say conductors. First conductors. C stands for conductors. Number 14. How many conductors number 14? 2. Multiply it by, what's the allowance for number 14? 2. What would that give you cubic inch? 4 cubic inch from the get-go. All right, great. Now let's go to conductors number 12. How many conductors number 12? 2. Multiplied by allowance for number 12? 2.25. Everybody knows where I get these? From that little table? Okay, anybody can give me the math for that? 4.5. 4.5 cubic inch. Keep going, Chad. Let's go to the clamps. Clamps. How many clamps? All clamps count as? 1. Based on? What's the largest? Thank you. So 2.25. What would that give you? 2.25 cubic inch. Huh? All the clamps. Doesn't matter how many. But they count based on the largest, though. All right. Grounding conductor. How many?
1.
All of them count as 1 based on 12 or 14? 12. So that based on 2.25, and that will get you again 2.25 cubic inch. All right. Am I done? No. Wishful thinking. Receptacle. The receptacle. How many receptacles? 1. Okay. Each receptacle have to be doubled. The devices have to be doubled. So that has to be multiplied by 2 from the get-go. And then the receptacles, which conductor is landing on the receptacle? 12. So we have to base it based on 12 or 14? 12. So that would be 2.25. And what would that give you? 4.5 cubic inch. Done, Chad. Let's switch. Okay, switch. How many switches? 1. Every switch always double it. The devices are always doubled. So we multiply by 2. And based it on what? The device, the conductor that's landing on it. Which one is landing on it? Number 14. So I'll give you 2. And that will give me 4 cubic inch. See how easy that is? Anything else need to be added in this box? Aaron? Nothing. Now if I have another conductor just sitting there, you count it based on whatever size that conductor is. Cool? All right. Can somebody be generous enough to do the math on all of them and give me the cubic inch for all these boys? 21 and a half or 21? 21 and a half cubic inch. Okay, now I did my math. Now I need to find, remember, it's 2 gang box. I need to go gang 2 things to give me this amount. So they're all device boxes. So let's look at my options for device boxes. And when I have, and I'm looking at the cubic inches right here, guys, cubic inches. So I'm looking, okay, 7.5. You double 7.5 is what? Start with the first one. 7.5 times 2, 15. Nope, small. The second underneath it, I can't read it. What's the second underneath it? 10. 10 times 2, 20. Is that good enough for 21? No. So what's the third one? 10.5 times 2, 21. Is this good enough? No. What's the third one? 12.5, right? 12.5 times 2, 25. Is this good enough for 21.5? Good. So what size conductor do I need? 12.5 box. I'm sorry. Box do I need? 12.5. That will translate 1, 2, 3, 4. 1, 2, 3, 4. That will be this box here. So it's a 3 by 2. Help me here by. Thank you. 2.5 inches. This is the single gang box that I need to gang. There's 2 of them. Yeah, because we gang it. See how we have 2 of them gangs together. That's it. See that rocket science, the box fill calculation? Any question, guys? Any question about that? So that's basically it. I wanted to show this example. Typically, I didn't do a whole lot of box fill calculation. I do the pole box calculation when we do commercial. But that will give you, is this good enough for the rest of you because it's a refresher? Aaron, you and I can do more if needed, when needed. Then they spice it up. They start how many conductors you can. If they ask you, okay, so we're good to this point, right? Let me tell you, add to it, spice it. I'm going to spice that boy. Now, how much cubic inches this guy can carry? We said 25, right? 25. There's 2 of them. The 2 of them can carry 25, right? And how much already occupied? 21. Here's my question for you, right? Up to this point, we are good. So Mr. Ryman decided to pull, he wants to pull a couple of conductors for future use. Just conductors. And the question is, they're all number 14. I want to pull conductors number 14. And I'm asking you, how many conductors number 14 I can bring to this box for future use, and I still meet the criteria for, I'm not going to change the box. How many extra conductors can I pull? Okay, let's do the math. So this is already occupied. This is the available. So you take the 25, subtract from it 21.5. Can anybody do the math for me? 3.5. The 3.5, this is the available space ready for me to occupy. Cool? Everybody's okay with that one? That's ready for me to occupy. Now I need to know, I need to translate this one from euros into dollars. Now, I don't know what 3.5 cubic inches means in terms of conductor. I need to see how many conductors. I decided to bring number 12, number 14. Number 14. So the next thing you do, so here's step 1. Step 2 is you take the 3.5 divided by, now, what's the cubic inches? Thank you, 2. For this boy, what's the math on that one? Give me the complete math. 1.75. Okay, can you pull a 0.75 of a conductor? No. So what's your answer is going to be? Only one conductor number 14 I can bring. Yes, sir.
Was he bringing them in there to add a device in the future, or was he just running them through?
In this case, it's meaningless bringing one conductor, really.
No, I'm saying, like, what was the purpose?
Yeah, there's no room to add anything else.
What was the purpose of him running the conductors through there? Just to go
The only thing I can think of is, what if I want to put this device into an isolated ground?
Could be an extra for a multi.
Isolated ground. Multi-wire, isolated ground. I want to split, or multi-wire branch circuit, split this receptacle into 2 circuits. But then you're going to change the wire because you're using 14.2 now, at 12.2. Well, in this case, I'm bringing 14. It really doesn't make sense the way I did it. You almost have to bring 12 to make this a multi-wire branch circuit. So circuit up, circuit down, or an isolated ground receptacle. Then you have to take the 14.2, throw it out the window, and bring 14.3. And sorry, 12.2, throw it out the window, bring 12.3. That's when you add that little device. Sense-wise, if it makes sense.
So you'll answer your question on memory though. If you do have conductors that pass through the box and there's no splice on it at all, it's just passing through, does it count as one?
One, unless you loop it with 12 inches or more. Then why would you loop 12 inches? You know what 12 inches is? It's a long 12 inches or more. You're blending into cutting it. Is this good enough? That makes sense? That's really as ugly as it gets in terms of box fill calculation. As ugly as it gets.
I thought if it went straight through the box, didn't have to hit just with the zero.
If it passed through the box, it's 1. No, not 0.
No matter how many conductors?
No, each one of them will
Each
count as
conductor
1.
will
Yeah. If you pass right through the box, or each conductor will count as 1. Each conductor. If you loop them 12 inches or more, each conductor will count as 2. That's in the general exam. Okay. All right, so I'm gonna go directly to. I know my time is up here. The last thing I want to do, guys, is the last thing I want to do. I'm gonna move here. I'm just got this one, this one, this one, this one, this one. Okay, we got these. Okay, we talked about these. Any question about these, guys? Any question about these? So the last thing I wanted to show you is a couple of rules. There is a table that has a couple of rules. Yeah. Keep going. The reason is heat. Heat. Pure heat and room, space. Heat and space. You don't want to jam too many where you can't fit them. Clamps. Okay, here. The last thing I want to talk about, guys, is this nice little table. So, box fill calculation. Any question about box fill calculation? We'll do more one-on-one if anybody wants more. There's a couple of good examples in the book. Please do them. The last thing I want to talk about, this table gives you the height. Now, how many receptacles do I need in a room? It's coming. We will talk about the rules 6 foot and 12 foot and 2 feet and in between. We'll talk about all these rules. This table is based on the American with Disability Act. You are not going to find it in the code. This is based on the height. The NEC code book, guys, doesn't talk much about how high off the finished floor you need to put a receptacle or an outlet. So as an engineer, we have to specify in our specification, how are we going to put these receptacles? Here's the guideline. For example, regular switches. Regular switches, look at that. It's 46 homeowner wants switches mounted. Unless they want it otherwise, you're going to mount it at 46 inches to center from finished floor. Okay? If they are as to be easy for children, you can use, if you want a receptacle for children in certain areas, you can put it 30 to 36 inches. Especially people with disability, 30 to 36 inches, they can be able to reach it. If there's no disability issues, typically 46 inches is, again, no code. There's no code. This is just comfort of reaching and flipping the switch. Cool? Let's look at between counter and kitchen top. Here's another recommendation. Look at these recommendations, guys. Receptacles, regular 12 inches to center from finished floor as you mount them. In the kitchen, here's your between 44 and 46. In the garage, look at the garage. In unfinished basement, in finished basement. How about outdoor, above grade? I don't agree with this one. Minnesota, remember we have snow, so maybe you push them up a little bit, a couple of feet higher than that, because they get buried by snow here. So these are, again, recommendations. So unless you know otherwise, this is a good location to put them. Outdoor entrance light, 72 inches to the side of the light or above the door. So these are all recommendations, guys, on the height of the switches. So could you please give me a thumbs up that we know it's there, Chad, and we can use it as a reference? Cool? Because you're not going to find it in the code. Remember, if you have the code says in dwelling, not dwelling. In dwelling, if you put a receptacle 5.5 feet higher than 5.5 feet from the finished floor, that receptacle would not count as part of your required receptacle space-wise. 5.5 feet would not count. So your plasma TV, you put 6 foot from the finished floor to your plasma TV. That receptacle does not count as one of the ones that you need in your living room. The 6/12 foot rule. We're going to go over, you have to put another receptacle down. Keep this in mind. So that's the height. Now, laying them out in a room is a different discussion. You guys know it, but we'll visit it another time. It's coming. Cool? Any question, guys, about this? That helpful a little bit? Refresh your mind, jog your memory for the box fill calculation. So do me a favor. I know this chapter is long, guys. Read it. It's really cool. It makes a lot of sense. So the tables I highlighted, please look at them, guys, because they're really cool, especially the table that lists all these requirements. All the stuff that we talked about is in the code. The book puts them in a nicer format. Any question? Cool. Let's have 5 minutes break, and then we'll continue, guys, with the CAD. And I apologize I took more time today because we weren't able to lecture on Monday, if you guys remember. So, all right.
It's all the same.
All the same. Yep.
One class, the other class.
Yeah. Absolutely.